Okay, so this is just a little bit about what we're doing today. And those of you that know anything about maths will say, well, that's not too fearsome, sir. Okay. But we do need to memorize these equations, annoyingly. They're not going to necessarily give them. And I'll talk in more detail about them in a sec. But just very briefly, as a starter, net primary production equals gross primary production minus respiration. And net production equals, I've forgotten what it is, feces plus respiration. Okay, I've forgotten what I stands for. This didn't used to be on the A-level course, but it's going to come up in a minute. And then the efficiency of biomass equals the biomass transferred to the next level divided by the biomass available at the previous level times 100. Okay, so let's crack on with the first one then. So there's something called primary productivity, and the clue's in the name of it about primary. Well, actually, no, that could be confused with primary consumer, isn't it? So we better be clear about this. So there's something called the gross primary productivity, which is the total amount of chemical energy converted from light energy by plants in a given area. And so you probably need to screenshot this or something, okay? And then, then we've got the term respiratory loss. And so respiratory loss, the gross primary productivity is your photosynthesis of a plant. And so GPP, the word primary means we're referring to the plant life at this point. We are not talking about the subsequent animal life that will depend on this plant life. So GPP and NPP refer to the plants, okay? And so there'll be a whole lot of sunlight reaching the earth that will never get even absorbed in a plant. And the reason for that is, as you've learned in photosynthesis, that plants tend to only absorb energy in a specific wavelength. So there's whole wavelengths of light that are not even being absorbed by the plant, and they're just being reflected. And so, for example, this is off at a tangent, but a lot of solar panels now, they're trying to get two materials in one solar panel to absorb two different frequencies of sunlight at the same time, to increase, if you like, the productivity of a solar panel. So that's going on right now quite effectively, making solar panels much better per meter squared. But plants, sunlight's abundant for plants in most situations, and so they just absorb in a certain wavelength. But even when they have absorbed and carried out photosynthesis and made glucose, some of that will be lost, and that is because plants respire night and day. Okay, and when you respire, that's a chemical reaction that's exothermic, gives out heat, and that heat is lost to the environment. And so that energy is not available to the next trophic level. And you can also think CO2, those of you who are chemists, CO2 is exiting at night. If you do your mass, relative atomic mass, you'll notice CO2 weighs more than oxygen. So we're losing mass at night as a plant. You will also be losing the energy in the bonds of CO2. But in general, we characterize this loss as all connected. It's all respiratory loss. And we normally characterize it as a heat loss in plants because an exothermic chemical reaction or a series of exothermic chemical reactions have occurred to produce ATP, and heat has been given out. So the plant has a respiratory loss, okay? And so what is left over after the respiration is gone is called the net primary productivity. You have the same thing in economics. You have you have gross profits and net profits. Your net profits are after you've paid all your costs or whatever, something like that. Okay, so let's look at this equation. Here's the equations. You won't get a simpler equation anywhere. It's just the net primary productivity is the gross primary productivity minus the respiratory loss of the plant. Okay. So this is expressed as a rate. And I told you the other day why that is, and the rate is per year. Okay. So let's think back as to how this is. No, sorry. Let me just say one thing. So the reason we do the year thing is if you just take this data at one particular time of year, it may not be very accurate. Okay. Over the year is a lot more accurate, and what I mean by that is I tried to explain this the other day, and then I thought a bit about it. So typically you might have a herbivore and its predator. I know we're talking about plants at the moment, the same might apply. And then you might have the predator. These herbivores have gone up huge in number, and then you'll find the predator numbers lag behind. Okay, and they lag behind. It's great drawing skills, and you'll note that at this point we've got an inversion of the biomass pyramid. Okay, we've got more predators than prey. And as I was trying to tell you yesterday, well, that situation cannot energetically is impossible. Okay, because as you go down the food chain, there are respiratory losses and feces losses. And so you can't have something for nothing in energy terms. There must be less biomass of predator than there are prey. It's impossible. But in this one particular moment, there might be more biomass of predator than prey. Okay, and I should probably have drawn those predator lines as lower in mass than the prey. So if you just take one point in the year, you'll get something that is thermodynamically weird. Okay, and so we do it as a rate, an unusual rate in that it's a rate over a year. Okay, and they can ask this is what units would you use? And so the second point to realize is they've gone kilojoules when all of your, or a lot of the pyramids you've seen at GCSE are biomass in kilograms. And so I talked about that last lesson as well. I said, well, kilojoules is more accurate than grams because energy does not necessarily equal to mass, although there's a correlation. In chemistry, we're more interested, the energy is in the bonds as much as in the mass. And the reason higher masses have more energy is because they have more bonds, okay? But it's possible for something like fat to have more energy per kilogram than something like glucose. And that is in fact the case. Well, how is that possible, sir? Well, the fat has more energy in the bonds. That must be the case. The only possible explanation where the extra energy is coming from, the energy is in the bonds. So joules are more accurate again than kilograms. And the other factor we're interested in is per meter squared or per HA per hectare squared, if we're looking at farming in particular. Okay, so we can also call this primary productivity. Now, we might want to think back. There's a lot of recapping, but that's fine. How do we even come up with this figure experimentally? Well, roughly you would, so let's look at these two figures again. How are these figures determined? You would determine how much time and resources you want to throw at it. Obviously, the more time and resources the more accurate your figure will be. Yes, Oscar?
I'm guessing let's do it by mass, but how would they do the energy if they want to look at animals as well? Because you can't really dry out an animal and burn it on a large scale. So would they just do it by mass, or do they have another way of finding it out?
They would do it by mass. You can kill, dry out.
Well, you could, but
And,
to do that on a large scale, surely
you
that'd be a
need,
bit unethical.
you need a big calorimeter. Well, here's the point. You put a lion in a calorimeter. Here's the point that we do. All ecology is approximated for the reasons of ethics. Okay, so so how one way we could measure these two figures, we could put a 10 meter tape measure by 10 meter and make a square of rainforest. Okay, then we could do our random numbers, and we put down a quadrat, Oscar, and we put out, I don't know, put the quadrat down at address 1, 3. Okay, we'd go 1 meter in one direction, 3 in another. We'd put down the quadrat. Okay, and then we would extract. I mean, God knows how do you do this in a forest, because there's trees you can't. You'd have to chop down a tree. You'd actually have to chop down a tree. So you'd put that quadrat down and kill all of the plants in that meter squared and lift them up and take them with you to the lab, okay? And then dry them out. As we said, put them in an oven at 100 degrees, heat them to constant mass, okay? And that will give you kilograms, and then you can put a certain amount of those kilograms into a calorimeter and turn it into joules. So that's how it would be done. Now, as I said, if you went with low accuracy but high ethics, you could just do, I don't know, probably five quadrats, remove all the stuff, including the animals. You'd separate the animals out in that. Now, obviously, they'd be, at that point, you say, well, how the heck do they measure the large carnivores? So it's beyond the scope of this, but to measure the large carnivores, you would at some point have to do one. You'd have to work out the biomass of one large carnivore, okay? And then you wouldn't have to do that experiment again. Instead, you'd do something called tag release recapture. So if you'd watch the animal, the way you count numbers of animals in an area is called tag release recapture, because they move. And we don't have time to talk about it now, but you'd put a mark on them and you'd see how many walk in and out of the area and how often, and from, obviously you probably have to determine their territories and all kinds. Probably would just track them, put traces on them, and but there are ways of estimating animal populations. Okay, so all that one needs to do is find the average energy in one and extrapolate to the numbers you've got. And it's the same here. All that one has to do is to find the energy in half a square meter of tropical rainforest, and then you can extrapolate it to the whole rainforest, is what's been done there. Okay, so does that answer what we'll do? I mean, obviously, if you're in the desert, you might keep putting your quadrat down and get sand, but and you might end up saying, well, I'm going to have to do more accuracy here because I keep getting a big zero, and there clearly is some productivity in this particular desert. Yeah, so that in a nutshell is how these calculations would be done, and it is worth discussing. Okay, so seeing in mind, I've just given you the equation. This is very, very straightforward. So let's have a look at this. So it says the grass in an ecosystem has a gross primary productivity of 20. So here we're just looking at one particular population within the ecosystem. 20,000 kilojoules per meter per year. Sorry, per meter squared per year. It loses 8,000 as heat from respiration. Calculate the net primary productivity of the graph in this ecosystem. So can you have your calculators, please? Tap that in and work that out for me dead quick. And then as soon as you've done that one, try question 2, okay? The net primary productivity in an area of tundra. Tundra is we're all watching the tundra at the moment. The tundra is mainly associated with northern Russia. It has something called permafrost, which lowers the productivity, but the reason we're all watching it is the idea that that permafrost will melt due to climate change and release tons of methane into the air, starting the next apocalypse. Okay, that's why we're worried about the tundra. Side note, can you quickly work out the gross primary productivity of the tundra, please, as well? So I'll get your calculators out, please, and I'll give you a couple of minutes to work those out. Obviously, number one is probably too easy for an A-level question. You all got your calculators? Charlotte, have you done the first one?
Yeah, is it 1,200?
12,000.
12,000.
Okay, good. So how did we, yeah, just 12,000, yeah. So that's a very easy question, folks. We just remember that GPP equals MPP minus respiration. And there it is. Okay. Liam, have you done number 2?
Yeah,
How did you do that?
I just added them.
Why would you add them?
Because you do. It's just how to rearrange it.
Thank you. I'm looking for the word rearrange. You have to rearrange that same equation. Whatever you do to the left-hand side of the equation, folks, you must do to the right-hand side of the equation. And so that's why Liam's got add. And so your final answer was?
4,050.
Okay. So there's the rearrangement. As Liam said, he's made GPP the subject by adding it to the other side, and he's come out with 4,050 kilojoules per year, and that's basic GCSE maths, folks. So as I said, looking at that, it's not too challenging, folks, compared with what you might face in chemistry or physics right about now. That's not too bad. Okay, so well done if you've got that. Right, so now let's look at consumers. Okay, we've already talked about this. So consumers get energy by ingesting plant material or animals that have eaten plant material. And so not all the chemical energy in the consumer's food is transferred. and so it's lost in various ways. So there's lots of plants that are quite indigestible or that we don't traditionally eat. We don't eat some plants' roots we do eat, such as potatoes, but often plants we don't eat their roots. Obviously, the bones have a mass and an energy, and nobody eats bones, so that energy is lost. Okay, so that's part of it. As we said, some parts of plants are indigestible and they come out as feces. Urine, remember, deamination in the liver, excess protein will come out as urea in the urine. Okay, protein is not particularly stored that much. Okay.
Wait, so could you go back for a sec?
Yeah. All right, can I move on?
Yeah.
So here's this second equation. This bit you need to screenshot or get down or learn. So I forgot what I was the, so this is now net production. We're not going to call this primary production because we're going to associate primary production with plants. So when we see net production, we're talking about the animals, okay, either herbivore or carnivore or omnivore, okay? And so what is the net production of that? For example, sheep would be an example. How much of the sheep is available potentially for the wolf or whatever eats the sheep? Okay, so it was the chemical energy in ingested food. Okay, so that's the plant matter that the sheep has eaten. Takeaway. So this is very similar to NPP, except now we've added feces as a loss. So as I spoke to you yesterday, the respiratory loss in animals takes many forms. You know, the animal moves around. We're going to class that as a respiratory loss because the muscles have moved due to respiration. Okay, so that's going to be a respiratory loss. The animal keeps warm by shivering. We're going to call that a respiratory loss. But in contrast to plants now, we've got to include the indigestibility of foodstuffs for herbivores, okay, and carnivores for that matter. So the indigestibility or overeating sometimes, inability to store perhaps some of the food eaten will come out in both feces and urine. Okay, and so that is a loss. That is not available to the next trophic level. It is, however, available for the decomposers. But in terms of human beings, it's the role of decomposers is really recycling everything. There is an energy loss there, and this is the equation for it. Okay, so it's exactly the same, but what we're saying about animals is there's two types of energy loss in animals. There's the respiratory loss now, and feces and urine loss. Okay, whereas with plants we categorize them as having just respiratory loss. They don't produce feces. They do produce waste CO2 at night. We're going to factor that in as respiratory. We're going to call that waste CO2 exiting the plant. We're going to call that respiratory loss as well. Okay. And so this is also called secondary production. Okay. So again, the maths there is not necessarily too complicated. And so the last equation, I said we'll talk about 3, is to calculate the efficiency of transfer between trophic levels. Okay. And so the equation that you need to know for that is as follows. Efficiency of biomass transfer equals biomass transferred to the next level divided by biomass available at the previous level times 100. And whereas you might think, you might be surprised, so I've done a calculation there. Between the grass and rabbit, you've got an 8.3% efficiency going on there. If you work out that one, I think you'll find that's more efficient, which might surprise you, but because obviously the respiratory losses in plants compared to animals are really low, okay? And that's because, you know, they don't move a lot. They reuse CO2 for photosynthesis. It's only really at night that they respire all the time and produce heat all the time. No, that is true. Sorry, don't get ahead of myself. So why is this efficient? The reason this efficiency is really quite low is the indigestibility of much of the plant material. That is the reason. That is perhaps a surprisingly low efficiency. Okay. Whereas can you all just work out the efficiency for me, please, between the rabbit and the fox using that? So just very easy this morning, that one. Just plug the numbers into the equation, folks, and work it out. What's the answer, Dulcie?
34.
34%?
Yeah.
Everyone agreement on that? I've not actually got the answer.
Yeah.
Good. Okay, so look at that, a massive increase in efficiency there. That's a surprise because this rabbit ran around. Well, it's digestibility, folks, and that's perhaps why we are omnivores and not vegetarians, isn't it? It's all very well eating plants, which, you know, I fully recommend a plant-based diet, but the rabbit meat is very digestible, isn't it? There's whole parts of that rabbit which are easy to digest. A lot of the plant material is indigestible. Grass, for example, you can't eat it. It's just completely indigestible to you. So eating it is pretty much a waste of time. There'll be vitamins and minerals, but we're going to give eating grass a miss because it's indigestible. And so that eating rabbit, however, that's pretty digestible. And so that's perhaps comes out in the figures. All right.